Welcome back. We are continuing on with our worksheet 4B3, which is the second consolidation worksheet for special relativity. In previous videos, we have done questions 1 through to 4. We're now going to focus in on questions 5 and 6. Okay. So question 5 has a cosmic particle traveling at 0.8 C. When moving, these particles are observed to have a decay rate of, not a decay rate, but a decay time of 5.5 microseconds. How long will the cosmic particle, take to decay when it's traveling at 0.49 Cs? Okay, that's 4 nines there. Okay, rightio. So this is a two-part question. So what we need to do is find the normal decay rate, the normal decay time, because this is a dilated time here, and then apply a second gamma factor to find the decay time at this speed here. So let's do that. Okay. So we've got, just let me straighten that up. Question 5 it is, sorry. We've got a decay time is equal to 5.5 microseconds when it's traveling at 0.8 C. Like always, we need to find the gamma factor. So the gamma factor of 0.8 C would equal 1 minus 0.8 squared. So that is 1 over the square root of 1 minus 0.8 squared. And it's 1.6 repeater. Okay. So this is a time dilation question. So we need to write down the time dilation formula, which says TV is equal to gamma T naught. Now, this 5.5 microseconds over here is the dilated time. Because this particle is moving at a relativistic speed, we observe it to decay in a longer time than it would normally be. So this is TV. So that's 5.5 microseconds equals gamma, which is 1.66 repeater, and T naught here. Okay. Now T naught will be measured in microseconds because this formula here respects the units. So T naught would equal 5.5 divided by 1.666. So putting that in, we get 5.5 divided by the answer, which is 3.3 microseconds. Okay. Right, so this is its true decay rate, if you want to call it that. It's the decay rate that it would be if we were to create this cosmic particle in a laboratory. It should decay in 3.3 microseconds. So now we're going to ask how long will it dilate if we were now going to travel at 0.49s, that's 999 C. Okay. So let's work out the gamma factor for this. So the gamma for 0.9999 C would equal 1 over the square root of 1 minus 0.9999 squared. Let's see what this number is going to be. I'll put 4 nines there, squared. And the gamma is a large number, which is 70.71. So that's 7.71245. Okay, so I just rounded that last one, so 445. Okay, I will just use that on the value there. Okay, so we now know that the proper time is 3.3 microseconds. So we want to find out what it would be dilated to if it was traveling at this speed here. So it would be gamma T naught again. So it's going to be 70.71245 times 3.3 microseconds. So it's this number there, there's the gamma, times 3.3. And so it's going to decay in a time of 233.4 6.35 microseconds. Okay, so that's question 5. Question 6 is a spacecraft travels at 0.85 C. Crew on board this craft measure 6.2 months to have passed when they send a radio distress signal back to Earth. Okay, so the spacecraft is traveling at this speed, and at the time equaling 6.2 months, they send the radio signal back. A, how far has the craft travelled away from Earth when it sends the signal? And B, the radio signal is sent from the craft to the Earth. How long will the radio signal take to reach Earth? Okay, so let's try and do that. So let's find out how far it is away first. So they've been travelling, so this is question 6. They've been travelling for 6.2 months at 0.85 C. So let's have a look at the distance. So velocity equals distance over time. So distance would equal velocity times time. Remember, there's no acceleration here, so I'm just using this simple formula here. I'm not using any of the equations of motion, which have A in it. Okay, so the distance will be equal to the velocity, which is 0.85 times 3 times 10 to the 8th times 6.2 months. Now this here is in meters per second, so I need months to be in seconds as well. So we are going to use a standard 30-day month, okay? That's the average month. So we're going to time it by 30. So that's the number of days. That's the number of days. Now each day has 24 hours, and every hour has 3,600 seconds. So let's find out how far we're away, which is 0.85 times 3 exponent 8 times 6.2 times 30 times 24 times 3600. Okay, so it's 4.1 or 4 point, I'll write it down as the true value first, 979 ... by 10 to the 15 meters away. Or we could simply round that, because this is all going to give me 4.1 by 10 to the 15 meters. Okay, so that's 6A. Okay. We now have the distance. The radio signal is now sent from the craft to the Earth. How long will the radio signal take to reach Earth? Okay, so let's have a look at this. Our craft now is, and here's the Earth over here. Good. Okay, the rest of the countries. The spacecraft is traveling forward at 0.85 C, according to the people on the craft. So let's start that again. According to people on Earth, the craft is traveling at 0.85 forward, or the people on the craft just see the Earth receding out of their back window of 0.85 C. Okay, so it depends on who you're going to talk about, you as the observer down here, or the person who's on the craft. Okay, now the question is asking, how long does it take for a signal which is coming here to move back to Earth? Well, this is testing the fundamental idea that the speed of light is the same in all frames of reference. So the speed here, the velocity, is going to be 3 by 10 to the 8th. It doesn't matter that the craft is moving forward or the Earth is moving backward. It's simply going to take the time for it to travel this distance with this speed. Okay, that's an 8 there. Okay, so the velocity is equal to distance over time. So time is distance over velocity. So it's simply going to be the distance that it's away is 4.1 by 10 to the 15 meters, divided by the velocity, which is 3 by 10 to the 8th. The reason why the question is here, I think, is simply to establish that you don't need gamma factors in this situation. It does not change. So dividing that there by 3 exponent 8, you get 13.65 by 10 to the 6 seconds. Okay. Oops, sorry, that's down there. So that's how many seconds it will take. Let's give this let's firstly divide that by 3,600, which is, let's just keep track of this. If that's how many seconds it is, it equals 3794.4 hours. I've just divided by 3,600, so that gives us into hours. Divided by 24 gives us how many days, which is 158.1 days. And dividing it by 30 is going to equal 5.27 months. Okay, so, oops, we've gone off screen. So it's 5.3 months for the distress signal to reach back to Earth. Okay, so that concludes the consolidation worksheet number 2. Thank you.